Continuing the development of a low-power wireless node, this time we'll go into powering it from a battery. But it needs 3.3 volts to operate properly, so how am I going to run this off of one or two regular AA, AAA cells? Many battery-powered projects I see use a lithium battery, and then there's a charge controller and all of that. I'm really looking for something simpler, regular disposable batteries, and so since I want to run this off of one or two AA cells for a long time, perhaps a year, that's going to take me a little bit of extra effort. One approach is to use a simple boost controller here. So I had to build a couple of those up and try them out. I have a couple working, but now I need to characterize them and check out their efficiency. Here's our general setup. We have the power supply that we're going to be using at the top, and it's going to measure the output voltage and current, which is going into the boost circuit. We will then have the boost circuit in the middle. This is a common ground. This is not an isolated device. This is not going to isolate the power from the input. And then on the output, we're going to go to the load through a DMM so that we can measure the current, and we're going to have another DMM to monitor the voltage in case there's anything interesting going on there, to make sure our boost circuit is stable all of the time. Now our input range is going to be 1 to 3 volts, and we're expecting a stable output of 3.2 volts all of the time at any input voltage and at any load. And our load is, initially we're just going to use a simple load of 22 microamps standby, which is about what the wireless node draws at that point when it's in sleep mode, and then 12 milliamps when the device goes active. The first boost converter I put together here was a simple one from Skyworks, the AAT1217, and it's a pretty straightforward little circuit to implement. If I can get that into some kind of focus here. There are two versions of it. One is of adjustable output, and I chose the fixed 3.3 out. There's really not much going on. You've got the chip in the middle. It's all integrated. There's nothing really much you have to do with it. You have your input voltage, an enable pin that you need to pull up. You need one inductor across the switch line to the voltage in, and all these little chips pretty much work the same way as far as that goes. You'll need an input power filter and of course an output filter cap, and that's it. So not much to do. They're pretty easy to assemble. This one I put together since it's a SOT23, I put it on a little breakout board and then soldered the various components directly onto it. I'll try and zoom that in a little bit and get a little more light. Here we have the little AAT1217 from Skyworks on a small breakout board. This is a SOT23. This is actually really a pretty small chip. I'm hoping it's in reasonably good focus here. A little hard to tell on my screen. And so I never thought my fingers were that big, but you can see from scale what that is. Here's a standard half-watt resistor. Right here we've got just the chip itself, and then this is the inductor, and it is strapped right across the switch and the ground pins, or sorry, not the ground, the switch and the voltage input pin. And on the back we have the two filter caps for the input voltage and the output, and so I've got it all soldered directly on there onto the breakout board, and that allowed me to keep all the connections really short. It isn't pretty, but I didn't have to etch a circuit board to get it to work. Alright, here we have the AAT1217 hooked up. We have the grounds connected from our power supply, input from our power coming in from our power supply. Here's our output line right here. The green one's our chip enable, and this is our output, and so we've hooked it up to our DMMs so we can monitor the output voltage and the current. And here's the current returning from the other DMM here and going into our load, which is just really a simple set of LEDs. So let's see what kind of efficiency we get. at, we'll start with the high, the 3 volts, and we see that we've got an input current of 15.5 milliamps, an output current of 12.6 at 3.262 volts. And our LEDs are glowing nice and brightly. So with a nice 3 volt input, we're getting pretty good efficiency. Well, it's not too bad. Now if we hook up to our standby load, which is just a little 150K resistor, you can see that our input is 360 milliamps or microamps, and that is just to get us a little 22 microamp output. So the efficiency of this particular device at low standby current is not all that great. It's using 100 and it's using 15 times the input to give me an output with only a boost of about 0.3 volts. So since this device is going to spend most of its time asleep, maybe this isn't the right chip. Let's try another one. Alright, this time I'm going to use the Texas Instruments TLV61220, and again it's same general layout here as far as the circuit goes. We have the inductor from the switch to the VN, the input filter, and the output filter. Here we just have a divider network for our feedback, so this is a fully adjustable type, and let's see how it does. So here we have the little tiny SOT23 again, a sizable inductor. I think at this point we're looking at a 47 microhenry, and then a couple of input capacitors, and that's about it. The output capacitor, pretty much it. I've added a couple extras to improve the noise output a little bit, and then our simple divider network here. All right, let's try out the TLV61220 from Texas Instruments. We've got it hooked up here. Here's our grounds, our output to the two DMMs to monitor our output voltage, our output current, and we'll go ahead and leave it set to 3 volts. We've got it set to 3 volts, and we'll fire it up, and the LEDs come on. We're at 28 milliamps this time going in, so it's a little less efficient maybe than the other one at full current. Let's check it at, let's dial it down to 2 volts. And what's our current? Our current is now 36 milliamps, and that's not too bad. But notice that our output voltage has dropped off, and so is our, of course, because it's voltage dependent load, our output current has dropped. That could just be due to the fact that I've built this on a breadboard. They're just terrible ways to do switch mode supplies. Got a lot of stray capacitance, extra stray inductance. The grounds aren't really coupled that well. I have added an extra ground wire here just to improve some of the grounding of it, but probably not doing that well. So I could probably improve that a little bit. Let's dial it back up to 3 volts and try the let's try the low current load. So with it hooked up on the low current load, we're drawing still 22 milliamps, or microamps, sorry, and it's only pulling off the power supply 64 microamps. So we're still not super efficient, but that's a lot better than 360. So that might work out. What I don't like is how the output voltage really dropped off. So let's go down to an input voltage in our sleep current of just 2 volts. Alright, so we're still getting our 3.3 volts, which is good at 22 and pulling our 22 microamps. We're now up to 130 microamps of input though. So, okay, as the batteries get pretty low, it's going to really start to increase our current draw. Okay, this chip might work. So I was looking in my bin of various switch mode converters and stuff, and I found this little breakout board. So from Sparkfun that I'd picked up at some point and hadn't used. So I've soldered some headers on it. Well, let's give it a try and see what we get. This is based upon the on semiconductor NCP1402 micro power switching regulator. So, and that's what I'm looking for. Kind of concerned that this thing is not going to be efficient at my low current, but it does take 1 to 3 volts input and should provide a steady 3.3 volt out. Let's try it. Here we have the NCP1402 all hooked up to our power from our main PSU. We've got our outputs, our meters hooked up to the output to again monitor all the current coming and going and the output voltage. So let's fire it up. Oh, we're hooked up to the load again, same load. And so if we fire that up at, we're at 2 volts, let's go to start out at 3 volts like the others. So we're fired up at 3 volts and nice bright LEDs. We're consuming 17.4 milliamps with an output voltage of 3.3 and an output current of 13 milliamps. So seems to be pretty good. Seems pretty efficient at my full load. Let's try it on our standby. Okay, hooked up to our standby power load, and it is drawing, wow, at 3 volts it's drawing 41 microamps, so pretty good. Only about double our output current. Again, we're still steady at a nice 3.3 volts. Let's try it at 2 volts input. What do we look like? Okay, well, we're drawing 75 microamps to get a 22 microamp output, again steady voltage. And let's try full current at 2 volts. So with my full load running, 13 milliamps again, so we didn't get that fade out that I got on the TI chip, and we're pulling, still putting out a nice steady 3.3 volts. With an input of 2 volts, we're pulling 26 milliamps, which isn't, that's double our output, but it's a lot better than what we were getting, especially on standby on that other one, 15 times or something. It was just awful. So that's pretty good. I like this. It's a lot more efficient than I had expected. Let's dial the power down to 1 volt. How low could I drain batteries? Well, if I used a pair of batteries to get 13 milliamps output, it's still nice and steady. The LEDs are still nice and bright. I'm pulling 53 milliamps. So what, 4 times in order to 4 times the input current to boost from 1 volt up to 3.3. Well, okay, that's probably more effective than I really should expect. And what's my standby current like at only 1 volt? So at 1 volt power into the converter, my standby current of 22 milliamps, or 22 microamps. And my input's 158 microamps. So this at 1 volt, this on semi at 1 volt is performing similarly to the Texas Instruments TLV 220 at when it was running at 2 volts. So I got to say the on semi, at least given that they've put it on a reference board, and I did not. I had it on a breadboard. That probably explains a lot of it. But the on semi, I think I might pick up some of those and continue my run my actual battery tests with that. So I really like it. Let's look at the full performance curve of the NCP1402. To do that, I can stand here and set the voltage output and manually turn the dial and increase it or decrease it by 0.1 with each turn, pause, etc. Or we can create a list and perform a sweep of the voltage between across a range. So let's give that a try. To set up a list, you can go into the menu system, select List, and you can either manually enter the values through the keypad, or you can go into the Keithley Kickstarter software, which is what I did, and I imported a simple CSV file from a spreadsheet, and the Kickstarter software downloaded the various lists into here. So I have one list here that is set with a 10-second dwell time, which I'll be running at some point to test the actual power consumption with the wireless node connected. I've got another list here, and you can have multiple of these. So we've got list 2, which has a voltage range that starts at 3 volts, and I've got it going down in 0.1 volt increments down to 0.7 volts with a current limit of 200 milliamps, which should be more than enough, and a dwell time of 1 second for each step. To run a list, you can just go to the home page. You'll want to make sure that your measurement is set to V plus I, so you need to go into here, make sure it's set to V plus I, then simply drop over a couple of menus to where you have the option for a list, and all I did was hit list. Pick which list you want to use. I have 2 loaded, A and B. So now what we're going to do is press list and run it on the testing the sleep power. Start out at 3, 2.7. We're at very low current. And you can see that as the voltage takes a step down, the converter power kind of drops out briefly as the very weak load sort of drains that output capacitor out. So by the time we get down from 7 down to 0.7 volts, we're at 115 microamps. So we're at 5 times our input roughly to get our 22 microamp output, and that's probably okay given I've completely wiped out a pair of AA batteries by the time I get to that. So I think the performance there is pretty good. Let's try it at full load, or what we think the full load might be. This should fire up the LEDs, and now let's try it out. We're getting 18 milliamps, 20. This is with about a 12, 13 milliamp load. 2.2 volts. Wow, 2 volts, 30 milliamps out. And by the time we're down into the 1.2, 40. And at 0.7 volts left in the batteries, we'd be at 45 milliamp output or input to the NCP to get a 12.5 milliamp output. Well, that's probably okay since this is just my periodic peak pulse output. So from a load perspective, I think the NCP1402 would do a great job for long-term power off of a pair of AA batteries for a little wireless node like this. I'm going to hook it up to some AA batteries and kind of see how it goes. Since the Keithley during a sweep also captures the data as the sweep runs, we can look through this data and graph it out, take a look and see how it works. So what we've captured here is 2 runs, one with the 22 microamp sleep load, and as the voltage dropped from 3 to 0.7 volts, we can see the current consumption. Now, at such a low power consumption, I think this is just the converter switching on and off periodically to charge that output capacitor, because really that load current just wouldn't drain that output capacitor very quickly. But we can see it kind of cross over and start to climb as we get into low voltages. At the 12.5 milliamp rough full load, as it drops from 3 down to 0.7 volts, we can see it evenly ramp up and really starts to gain power starts to increase in power consumption right in here as the node passes the about the 1.5 volt line right here. We can see it begin to really grow, and not sure what's happening here at the end. I think in that last step of the sweep I might have bumped the converter as I was switching it off, so I'll have to look at that. But we can clearly see how the power consumption, how the current consumption ramps up as the voltage drops off. So as long as my batteries are above about 1.5 volts for the pair, it looks like I should be getting pretty good current performance out of the switch mode boost converter. We've looked at the AA1217 from Skyworks, the TLV61220 from Texas Instruments, and the NCP1402 from onsemi, and I've run some multi-day tests with the NCP1402, and so far it looks promising. They've held a pretty steady 2.926, 2.927 voltage for days, so I'm going to keep doing some more tests. I'm going to look at putting some more of the 1402 converters together on some boards and running these at different loads to monitor battery life. Given how well the 1402 has performed, I'm going to move on to next parts of the wireless node, including improved performance and additional sensors. Currently, this thing is set to wake up every 8 seconds, which is fine for many applications, but for a door sensor, I think it should be every second or two. And then how will it be affected if I add temperature and humidity sensors to it? What will that do to the power consumption? In the previous video, I used the 2280S power supply to characterize power consumption, and we saw that the node powers up, transmits, and then shuts down very quickly. So quickly that the only meter that could really show it clearly was the power supply. So what I would really like to do is characterize the power consumption of the node at the code level. What we've got is an initialization routine, a sleep routine that also that not only shuts down the I/O pins, SD, brownout, all those sorts of things, lets it sleep, wakes it up as well, has the wake up routines, then of course the ability to transmit, and then all of that is run inside a main loop. Variety of things that need to be figured out are, should it only power up the SPI or I2C bus if absolutely needed? If the node uses its built-in ADC for sensors, or to monitor the battery level, what is the power cost for that, both in time and increased current? Are some functions taking longer or taking more power? What is the effect on power for each code change? So as I go through and change the code, I'd like to be able to see real-time how did that affect the power consumption. The way to really measure that kind of power consumption would be a high-speed DMM. Not just the faster brother of this lowly 34410A. Things like the 34411A and the 34470 will go up to 50,000 samples per second. No, we want something with serious speed, maybe 1 million samples per second. Something like the Keithley 7510. But as it goes, I don't have one of those. But it's on my list to get. Thanks for watching. There will be more to come.